Okay, we're going to get started. Our next speaker is Ed Benowitz, who's going to give an overview of the SMAP Science Data Manager.
Thanks a lot. Welcome, everyone. Good afternoon. I'm a SMAP flight software developer, and so I'm going to chat with you a little bit about the Science Data Manager module that I was responsible for. And we're going to go over kind of from the top all the way down. So we'll start off with a little overview of the SMAP mission, and I'll tell you some of the instruments that are going to be feeding my software module some data. And then we'll talk a little bit about the data flow itself and the design of that. We'll talk about how the data is flowing through the hardware and what software is responsible for. And later on, we'll go down a little bit to give you a flavor of the implementation, talking about the interactions, the flight software responsibilities, and just give you a few metrics to give you an idea of what the software effort was. Okay. So here's the little overview of the SMAP mission. It's the Earth Orbiter, and SMAP stands for Soil Moisture Active Passive. And the overall goal of the mission is to provide measurements of soil moisture throughout the world. And there's a lot of benefits to getting that measurement, understanding the water cycle, the energy cycle, carbon cycles, help with weather prediction, flood prediction, and just assisting with climate models in general. So there's quite a few customers of the data. I thought I'd entertain you a little bit with a movie here that shows you what the SMAP spacecraft will look like. So there we are. You can see it involves an upper spinning portion, and we have a reflector boom. It should be coming to view soon. And we'll talk a little bit about the instruments, but basically as the reflector spins, we're gathering data over Earth. And the actual spacecraft computer is in that smaller non-spinning portion that you can see by the solar panels. So by spinning in this way, eventually can cover a wide area of Earth. It's kind of fascinating to see this being assembled little by little in our high bay. Okay, and kind of gives you an idea of what the final product will be, that final map. Okay, so on board there are two science instruments: the radar, which has a higher resolution but lower soil moisture accuracy, and the radiometer, which has higher soil moisture accuracy but coarse resolution. And the ground software is going to be processing the two data sets together, and in the end it's going to result in improved resolution by basically combining the data together. So from this is all actually from the SMAP website. You can get more details there about the science itself. And they get a spatial resolution of 10 kilometers and freeze thaw state, at 3 kilometers. And in the video, we saw the reflector spinning, and that's going to be spinning at 14.6 RPM. So you've kind of seen the mission overview, and the instruments that I'm going to be talking to are the SAR instrument and the RAD instrument, and they're going to be providing us with the science data. And this is really what my job is all about, is bookkeeping and dealing with the science data produced by these two instruments. So you're going to see SAR and RAD a lot. Just remember, those are the two instruments. Okay. So this is kind of an abstract cartoon here showing you the data flow at a very high level. We have the spacecraft on the left and the ground system on the right. And this is one-directional science data flow, so we're going from the spacecraft to the ground system. And now if we sort of zoom in on the spacecraft and see some of the important parts in the orchestration of this, we see the two instruments I talked about on the left. So the SAR and the RAD. And they have data that goes into our command and data handling box, C&DH for short. And then out of the command and data handling box, the data flows to the X-band radio. Okay, so that's kind of the high-level picture. Okay, and now we're going to, so throughout the talk, I'm kind of starting off at a high level and zooming in and opening up boxes and giving you more details as we go. So we're going to keep zooming in on this picture and adding more detail as we go. Okay, so this is that same command and data handling box that I showed you in the prior picture. But now we're opening up. Okay, and this is an actual piece of hardware, an actual hardware box. Okay, so inside this box, there are boards. So one board is our flight computer, which is the standard RAD 750 that others of you have known to love and use. And we have another board here, which is just called the NVM board. Okay, and now I'll delve, opening that box up a little bit more, talking about what lives within our NVM storage board. So we do have non-volatile memory. Okay, so you can think of that as several chips of NVM. We have RAM, which is non-volatile. We have a DMA engine, and we have instrument interfaces, so to the SAR and RAD, as we talked about before. And we have an interface to the X-band. Okay, so this has all our connections. And notice here, when I talk about the DMA engine here, we're not talking about a DMA engine on the flight computer board. We're talking about DMA, RAM, and non-volatile storage. And this is all on the separate non-volatile memory board, not the flight computer board. Okay, and that's one of the key ideas of this talk is where the data lives and where it flows to. Okay, so now within the NVM board, now we're opening it up the box even more. I'm showing you how the data flows. So the instruments have a physical connector that goes right into the NVM board. Okay, and that's the SAR instrument interface and the RAD instrument interface. And data flows from those instrument interfaces directly into FIFOs. Okay, so these FIFOs are specially allocated regions of the RAM on the non-volatile memory board. Okay, and the hardware has enough smarts to take the data coming over, say, something like a serial interface, and put it into the FIFO and maintain the FIFO pointers. Okay, so the next step is once the data is in the RAM FIFO, right? If we took a reboot at that point, the data would be gone. So we need to save it to non-volatile memory. So what happens is we're going to use the onboard DMA engines on the non-volatile memory storage board to DMA over the instrument data, which is now living inside a FIFO. Okay, and we're going to DMA that data over into the non-volatile memory. And if we took a reboot at that point, the data is still there. Okay? And so they all have their separate regions, and all the data is moved within the board. And that's the key point, is the data has never left the board yet. Okay? It comes in from the instrument directly, and it stays within the board. Okay? So now we have it in their respective regions of non-volatile memory storage. Okay. Now we have the data saved. Now the question is, how do we get it out? Okay. So as you recall from before, we have our data, SAR and RAD, in the non-volatile memory. And again, the data hasn't left the board yet. We're going to do another DMA. Okay, and this DMA is from non-volatile memory to another FIFO allocated within the RAM, which is still in the NVM storage board. Okay, and this is called the collector FIFO. And basically, this FIFO collects the science data out of NVM, stores it in RAM, and the next step is getting that data out of the volatile memory of RAM and out of the X-band interface. Okay, and so we have hardware that's going to, all within the NVM board, that's going to take care of this for us. Okay. So one key point here is that the science data itself is never seen on the flight computer board. The RAD 750 does not see the science data at all. The NVM board is going to store and buffer and prepare the science data for transmission. And the flight software, instead of going through the data byte by byte, okay, what it's going to do is basically orchestrate and command the NVM board and coordinate the movement within the NVM board, kicking off, for example, DMAs. So on the input side, what flight software will get is an interrupt. Okay, it will get an interrupt from one of those input FIFOs. That was the first step, is data comes in over a serial port to the input FIFOs. And when the FIFO data is slowly growing, and when it reaches a certain mark, we're going to get an interrupt. So that interrupt from the NVM board to the flight computer will tell us data has arrived. It's time to do something with it. So in response to that, flight software is going to ask the hardware to DMA from the instrument input FIFO into NVM. And by the way, flight software is telling it, flight software keeps track of the actual NVM addresses. Okay. And on the output side, it's a similar story, but almost in reverse. The ground will tell flight software, I'd like to transmit data, get ready for a pass. And so what flight software is going to do in response to that command is it will ask for a DMA, but this time on the other side, taking data out of the non-volatile memory and into the collector FIFO. And remember, the collector FIFO buffers the data before it goes out to X-band. So X-band will start basically clocking out the data out of the FIFO. And when it gets below a certain level, the FIFO within the NVM board will give an interrupt. So the interrupt goes from the NVM board to the flight computer. Flight computer sees we need to get more data into the collector FIFO. And so in response, it will request a DMA. And so the process repeats and repeats. The data shrinks, we get to a certain level, interrupt happens, and then flight software fills us up again. So it's that constant process of data going up and down, getting an interrupt, doing another DMA. So this is all happening continuously, both the input and output side. And basically, we repeat this process until there's no more data left for the particular COM-pass. Say, COM-pass might have a certain time duration, for example. So we'll call it the end of the pass at that point. So a little more on the responsibilities of flight software in this case. As I mentioned before, this is all high-rate data, and all this has to happen simultaneously. Now, of course, in hardware, there's a limited number of DMA engines. And as I mentioned before, there are potentially 3 DMAs that might like to happen at the same time. But we have limited hardware resources. So it's flight software's responsibility to arbitrate between the possible 3 requesters of the DMA engine and perhaps a fewer number of DMA engines actually available in hardware for use. So flight software has to arbitrate that resource. In addition to just determining who gets to use the DMA engines, flight software also needs to provide addresses for every DMA operation. Those addresses, of course, are within the NVM board. So there'll be NVM board addresses. And so when software requests a DMA to the hardware, it's going to essentially pass along to the hardware over the interface between the cards, say in registers. What addresses shall we use for the DMA? And so the flight software has to maintain an abstraction on top of what hardware is doing. In fact, what the abstraction that flight software is providing is actually one huge non-volatile FIFO. Okay, so even though it's implemented with DMAs and smaller RAM FIFOs and a large address space of NVM, flight software has to divide up the NVM address space, has to make this whole process, this whole machine, appear as one giant FIFO. And our policy is to not overwrite old data. So as we're marching through non-volatile memory, we get all the way to the end and wrap around. And when we fill up, we need to stop writing data. Another flight software responsibility is keeping the SAR and RAD regions within an NVM completely separate. To the NVM board, the actual non-volatile memory storage is just a bunch of bytes that's addressable. And so we need to provide and keep separate the SAR and RAD regions. We also need to manage the locations within SDRAM of the FIFOs. And there are control registers that are set by flight software to control the FIFO size and various properties about when we get interrupted, for example. So that configuration and abstraction is provided by flight software. One requirement we also have is the need to overlap data in the transmit. This was asked for to facilitate the ground processing of data. If you know there's overlap of various passes, it makes it easier for the tools to stitch the data together. So requirement for flight software is transmit a bunch of data, and on the second transmit command, replay some amount of data from the tail end. And that would make the ground system and the ground folks happier. So we'll be happy to oblige. All right. Another item I talked about before was transmission and also retransmission. Because the data is stored in non-volatile memory, if perhaps some data was missed, say there was a problem on the ground, or for some reason the transmission didn't work, we also provide the capability to retransmit science data that was already saved. And so we provide several commands to allow that to happen with various priorities of data that the ground can select. We also provide telemetry. So we get periodic telemetry showing perhaps the state of FIFO, how much data is left in non-volatile memory, for example, so the ground can know how much data they still need to transmit, for example. And we also provide local fault monitoring and responses, and we'll talk about that in just a bit. I wanted to compare and contrast with you just a typical rough overview of what a flash file system would look like versus what we have here in the SMAP Science Data Manager. So what we provide is not a file system. It's basically, for SMAP, it's abstractly, you could think of it as a FIFO backed by some non-volatile storage. Okay, so let me walk you through my comparison to give you a data point for comparing the two. Okay, so in both systems, and this is a property of the hardware really, blocks have to be erased before they're written to. And so there's special code in my software that gives us a certain amount of erasing before we write our actual science data, and that's part of the abstraction that we provide. And so a file system would have to do something similar. Another property of the media is bad blocks. Typically, you would get a list of bad blocks from a manufacturer, and so you don't want to use those. And so as we're incrementing our pointers along, marching through NVM address space, you can't just increment one and call it a day, because we need to maintain that bad block list in software, look at it before we choose to use a particular block, and and avoid it. So that's another issue that makes the software more interesting. Now, and that's a property of both a non-volatile file system and what we're doing on SMAP for the science data. Now, at this point, the file system and our sort of FIFO start to diverge a bit. In a typical file system is, of course, random access. You can read and write files all over the place. With us, however, it's a FIFO. So with the exception of, say, bad blocks, right, all the data is written consecutively. It may wrap around over, but there's no need for random access. So that helps us out. You could imagine, right, having an easy way to march through all the DMA addresses were probably very close to sequential. So makes the DMAs a bit easier to think about. In terms of where leveling, this is definitely an issue for a typical file system, but for us, it's not so much an issue. In a file system, when you're writing to NVM, typically you have a certain number of write cycles, a certain number of burns you get, and after that, good luck. So what the typical approach for a file system to do is, instead of hammering, let's say there's one file that you happen to access quite a bit and changes quite often. If you left the file in the same block, you'd be write, erasing, read, cycling that one particular block over and over again, and that particular block would get worn out faster than everything else. So a file system would probably want to spread out the writes across the media, so that where it's relatively level, and so overall, you get more life out of your hardware. Now, in our case, because it's a FIFO, as I said, we're sort of marching around in a circle, right? We're not writing to the same region over and over again. So for us, we deal with where leveling automatically because it is a FIFO. Okay. So our reads and writes are going to be very even. So just a little bit of feedback on the software statistics. It's about 7K lines of code, physical, 3K logical, 3K lines of comments. This is really a topic for a whole other talk, but this code was auto-coded using a state chart autocoder. So I actually drew all the states out in Magic Draw, and we have an in-house autocoder tool. Click a button, and out pops code. And so there are actually quite a few states to manage the DMAs and the addressing and setting up the X-band. And so what started off seeming like a simple state machine always expands into a more complicated one, especially when you get to the fault handling. So actually, it was quite useful for me to have that. And the code I actually ended up writing was more lower level things about interfacing directly to the registers, or maintaining the bookkeeping for what address I should use next. But the sort of flow of the code through various states that portion was auto-coded. And within my module, I sort of I fenced off the code into 3 regions, basically. One exclusively dealt with science data input. One exclusively dealt with the other side, which was the output side and the transmission out of X-band. I had one that just abstracted the addresses, and how do you increment an address properly while avoiding bad blocks and wrapping around. So that kept track of read addresses, write addresses, and erase addresses, and ensured that I did all my erases first before I did my writes, because that's a requirement. And just an overview of the SMAP flight software. We just, in general, used inter-process communication for dealing with other modules, so, for example, commanding and whatnot. And when I get an interrupt, that message comes onto a queue, and then I take the message off the queue and process the interrupt. So local fault protection. All of the fault protection that we're doing related to science data is actually located within the module. So for this particular one, we didn't need to go up to a higher level, do anything at the system level. Just about all the 4 categories of things that we need to make it work each of them could possibly go wrong. So for a DMA, for example, we could fail in various ways. Maybe we DMA part of the data. Maybe we tried to DMA into an invalid address, for example. So we have to deal with DMA failures, single bit errors, double bit errors. What do we do about those? Besides that, we could have various errors on the FIFOs. In RAM, we have input FIFOs and collector FIFOs. And because it is a limited size, right, you could always overflow it. Or as you're reading from it, you could hit the bottom and have an empty FIFO condition. Right, you could, as you're programming it and setting the boundaries of the FIFO, you could perhaps try to program it with an invalid address. So anyway, we have handling for all those situations. We could also have a problem with the X-band radio. It could unexpectedly get turned off, or it could be malfunctioning while we're transmitting science data. And so we need to deal with that situation as well. And as far as responses, we do have a relatively limited vocabulary of what we can do, but here's some menu of choices. We can empty a FIFO out, clear it out, program the registers, set the size to 0. We can reset a particular hardware interface. So there's serial inputs and outputs to the X-band radio and to from the instrument, so we can always reset an interface. And if we're in the middle of a transmit command, we can abort the command itself. So those are the local responses. But this is all isolated to within the Science Data Manager. We don't have to resort to pointing the spacecraft in another direction or anything like that. So it's all handled locally. So what I'm hoping you take away from this, what I'm hoping you take away from this is, we had a high rate data requirement, and one way approach to that was really to have hardware in the loop. Hardware taking a very large responsibility for data storage, transmission, and keeping the data out of the flight computer itself. And just having the flight computer basically being a conductor, orchestrating the hardware, orchestrating the DMAs, keeping track of the addresses and doing some arbitration, but not actually going byte by byte through the data. And I think that's something that could potentially be used in other scenarios as well. I'm sure there's a long history of doing this, but wanted to let you know about that. And so, you could see the interplay between flight software and hardware. And with flight software, orchestrating the hardware actions. And then on top of that, providing this abstraction for the ground that's essentially a big NVM FIFO that won't overwrite old data. And that hides away all the details about what the hardware is doing behind the curtains. All right, well, that should do it. Are there any questions I can answer? Oh.
Do you have to do any compression with the data, or since you're going directly to the hardware device, you're obviously not doing any software compression? Is there any hardware compression, or do you just not need to do it?
Well, to us, the data coming out of the instrument is an array of bytes. So whether or not compression happens on the instrument is transparent to us. Yeah.
You were mentioning about the flash file system, but you didn't necessarily say what you were storing, what SMAP was based on. Is it also flash?
So, there might have been two questions there. Do we have an additional file system? Is that
No,
what?
do you have, how are you storing the data that it's non-volatile? What kind of hardware, physical hardware?
Not sure how to answer that particularly. We have banks of non-volatile memory. Is that what you're?
Yeah. So it's
NAND? Is that what you're getting at?
Pardon? Okay. So all right. Yeah.
Okay.
But I'm just wondering about any kind of radiation. Is that all accommodated in the devices themselves?
Oh, I see. EDAC. Yes.
Yeah, yeah.
Yes. There's some onboard EDAC. And it's actually very transparent to the flight software, which is good. But yes, there are extra check bits. Yeah, yeah.
I was just curious about operationally, since you won't override anything until apparently you've transmitted it down via X-band. Do you can you store that much? That could get you into some strange situations if you haven't had a downlink in a while.
That's very true. We do have a very hefty amount of storage because data is such high rate. So I can't give you the exact number, but we have gobs and gobs, shall I say. Yeah, for RTI reasons, I don't think I can give you the exact number.
Fair enough.
Yeah.
Yes.
So I was going to ask sort of the same question. So maybe could you give us an order of magnitude for the data rate?
The answer is no.
Oh, the data rate.
Yeah.
Probably hundreds of megabits.
Per second. Okay. What is the? Can you tell us the orbit?
I don't have the.
You can say no. I just.
Well, I think it's polar, but that's the extent of my knowledge on that one.
All right. Thank you.
Very good. Any other questions? No? Very good. Thank you.
Sure.